Well, hello, and we're back. So we've been talking about populations, and within that population, measuring and thinking about, considering a proportion that has a certain attribute, or a mean that has a certain attribute. Proportions would be categorical things like the proportion of all adults that are left-handed, right? And a mean would be something we can measure more quantitative, like heights of all adults. And as we said, we can't really measure everybody in a population, so we're going to take a sample. All right. And so we've talked about proportions and the distribution of those samples, right? Today we're going to talk about means. And so what we've got is we've got a population. And what we're going to do is we're going to take a bunch of samples of that population. So the story, let's go back to heights. And let's say we're doing the average height of 18 to 29-year-olds. Every 18 to 29-year-old on the planet. Impossible to measure. But we're going to do samples. And let's say we do samples of 1,000. And then we take the average of those samples. Now, those are simple random samples, so I'm not simply measuring the heights of the players on the Boston Celtics, right? We're going to do a nice random sample. Here's the key. First thought. If we take the average of all those averages, right? So you've got the average of the sample here, sample average here, sample average here. If we then average those averages, we should get the mean of the population. First thought. We know that there's a standard deviation associated with all of those means. And that's going to be the standard deviation of the population divided by the square root of little n, this population size. Now, again, we're not to the point yet where we're going to use just the samples. So for these problems at this introductory part, we're assuming we know both the population mean and the population standard deviation. An example of that might be your standardized test scores, right? We know the average for the overall population, and we're going to talk about a sample. But these are the first two big thoughts. What do we notice here? As n increases, the standard deviation decreases. Certainly, right? Because, or the standard deviation of the samples. So look, n is getting bigger, right? That's a bigger denominator. What happens in a fraction when you have a bigger denominator? The value of the fraction gets smaller. So if you want the standard deviation of your sampling distribution to be smaller, you can increase the size of n. Okay, now, before we do an example, let's talk about really the key topic with sampling distributions of means. And that's the central limit theorem. And it is what is going to allow us to solve all of these problems. Because you guessed it, much like the proportions, we're going to be using a normal distribution here. And here's what the central limit theorem says. It says, look, one, if your population is normally distributed, then your sample distribution will be as well. Then all of your x bars will also be normally distributed regardless of the size of n. Will be normally distributed no matter the size of n. Okay, well, all right, that's not that profound because if I'm dealing, say, with, I don't know, birth weight of babies, right? Certainly the population right? Baby's birth weight is normally distributed. You have a whole bunch that are about the same size, a few on this end and a few on that end. If I then take a simple random sample of 30 babies, right, that will also be normally distributed. But this next statement is really the key part of the central limit theorem. And it goes a little something like this. It says, look, even if the population is not normal, that's okay, as long as n is big enough. So if the population is not normal, the x bars will still be normally distributed. As long as n is big enough. And now what's big enough? Well, we generally like to think as long as your sample is more than 30, you're going to be okay. All right? And so if you're dealing with a population that is not normally distributed, we're going to see this as an example here in just a second, you have to make sure you choose a big enough sample. And here's the key theorem. And some people think this is the most important theorem in all of inferential statistics. If your sample size is big enough, the results of your sample will be normally distributed. Now, why is that important? Because then we can figure out how good those results are. Let's take a look at an example. But this, the central limit theorem, and you can Google this and read about it and watch more lectures on it. But the key idea here is, as long as n is big enough, your x bars are going to be normally distributed. Period. Well, that's a pretty helpful thought. All right, and big enough, we're going to use greater than or equal to 30. All right. So, I don't know about you, but it always helps me to take a look at an example. So let's look at one here today. All right. Household size in the United States. Okay, household size in the United States. Now, do you think this would be normally distributed? So based on the previous censuses, we know that the household size has a mean of 2.6 with a standard deviation of 1.4. But do you think we're normally distributed around 2.6? No, we're not. Think about it. Certainly you've got some people who live together in groups, some families, right? And they might have 4, 5, 6 people. But what else do you have? You have a whole lot of single people, right? And really, until recently, they lived by themselves in apartments. Now, of course, they all live in their parents' basement, but that's a separate issue. You have a whole lot of people living by themselves. So you've got a whole bunch of ones, and then you've got your family units, or what we would call the family unit. So this is not normally distributed. In fact, if you think about it, put your big toe up on the board for your right foot, we're going to be skewed right. So the distribution, the population is skewed right. Because you've got all those ones. And then you have, a bunch of people with 8, 9 people living in their house, right? So you've got a bunch of ones. But here's the thing, right? One, find the probability that a random household has more than 3 people. Well, you think, well, can't we just do the normal distribution, find my z, 3 minus 2.6 divided by 1.4 and blah, 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 blah? No, because we're not normally distributed. Can't do it. No, can't do it. Why? Because household size is not normally distributed. But here's what we can do. Let's choose SRS of n equal to, say, 100 households. Now, find the probability that the mean of those 100s, x bar, will be greater than 3. Can we do that? Yes, we can. That's the beauty of the central limit theorem. Because here's the thing. When you choose enough households, the distribution within that group will be normal. That's what's kind of cool, because you've chosen enough. You've done a random sample. So let's see how this works. Okay, so now this all comes together pretty nicely. You've got your mean is 2.6. Now, the standard deviation of our sample here is going to be the standard deviation, 1.4, divided by the square root of the sample size. 1.4 over 10 on my planet, that's 0.14. Well, now we're ready to go. Why? Because 100 is greater than or equal to 30. Therefore, the x bars are normally distributed. Boom. And certainly 100 is less than 10% of all households, right? We always have that caveat. That's back from our proportions. Okay, so let's finish this up now. We've got a z. Our z is going to be 3 minus 2.6 divided by 0.14, right? So this works out nicely. This comes out to be about 2.86, I believe. We can check that on the calculator. You can check that as well. Okay, so that's 0.4 divided by 0.14. Yes, about 2.86. So we'll say approximately 2.86. So there's my z. Second step, of course, is to draw our normal curve. Can I squeeze this in down here? Here's my mean. That's 0. That corresponds with 2.6. Now, 2.86 is going to be way up here, right? 1, 2, 3. So, and I'm looking for this little region out here. All right, and this is the region above 2.86, which corresponds to 3. So in this sample of 100, what's the probability we're going to pick out a household with more than 3 people? It's small, right? But it's about, this comes out to 0.0021. So probability that our mean will be more than 3 is approximately 0.21%. All right, and this is how we're going to answer this question. All right, sampling distribution with means. There's a nice summary of all these formulas with all of the conditions located most places on the internet. And maybe I'll do another one here in the next video, but if you take this problem together with the problem we did earlier on proportions, this is what we're working on. Good luck. See you next time.